BC Chemistry, Unit 4, Organic Reactions. This is when the memory game truly starts. The study design requires us to know and actually memorize, including reactants, products, and conditions for certain type of organic reactions, including oxidation, substitution, addition, hydrolysis, and condensation reactions. So, to help you better comprehend, in this chapter, chapter 11, I want you to pay attention to the bonds that are broken in each reaction and those that are newly formed. That will help you to understand the mechanics of the reaction a little bit better. A general trend for old bond breaking and new bond form is that double bonds tend to break to form single bonds, and polar covalent bonds also tend to break and form new bonds. Okay. You should also be attentive to special conditions such as temperature, UV light, or catalyst, or even acidify something. And think of a simple compound with 2 or 3 carbons for each type of reaction will help you memorize. When you are able to draw a mind map like this one without any help from your textbook or your notes, then you are almost there. Okay, let's start with our first type of reaction, substitution. Okay, so substitution of haloalkanes by halogens. Here is one example of the reaction equation. Okay, so it is about replacing a hydrogen atom on an alkane with another atom or group. Okay, so recall that alkanes are saturated. So if you want to change anything, you can only do so by replacing what's already in it, namely hydrogens. So alkanes are nonpolar and quite stable, and they are so abundant on Earth. So they don't really easily react, but we want to use them, right? So we need a little bit of initiation. Therefore, substitution of alkanes by halogens requires UV light. This condition is almost a signature of this type of reaction. So here, I show you 4 different steps. The halogens can be substituted into any or all of the positions, as long as there are enough halogens available. However, one molecule of halogens can only substitute one hydrogen from the alkane each time. So you will see that each time there will be one hydrogen-carbon bond broken, one halogen bond, in this case chlorine-chlorine bond broken, and then a new bond will form between the hydrogen and one of the chlorines to produce a halogen, and another new bond will form between this carbon that has just lost hydrogen with one of the halogens. Okay? So this is the first step. If you are to actually replace another hydrogen, you need to make sure that first of all of the methane in your reaction mixture has all reacted, and if you have leftover halogens, then the second step of the reaction will kickstart. Hydrogen halide is produced by this reaction, and once they're produced, their job is done. They cannot further substitute for another hydrogen on alkane. That means, for example, if you have 1 mole of methane and 1 mole of chlorine, once they completely reacted under UV light, then you will have just pure bunch of chloromethane and maybe hydrogen chloride as a byproduct. But if you have 1 mole of methane and more than 1 mole of chlorine, let's say 1.5 mole of chlorine, then your products will have a mixture of chloromethane and dichloromethane. So the dichloromethane is the product of the reaction of chloromethane and the excess chlorine gas in the reaction mixture. Okay, so the second step of the reaction don't start until the first step has completed. Okay. If at the end you have a mixture of haloalkanes as your products, then they can be separated by fractional distillation. Okay. Once we have haloalkanes, then we can further substitute them to produce more exciting stuff. Remember, the polar bonds between the halogens and carbons are more likely to be broken. Okay? So compared to alkanes, haloalkanes are more reactive due to the difference in electron-activity. The carbon-chlorine bond, or in many other cases, carbon-bromine bond or carbon-iodide bond, or even carbon-fluorine bond, is highly polarized. As a result, the partial positive center of carbon are vulnerable to the attack of a partially or completely negatively charged particles, such as hydroxide or even just ammonia, where the lone pair and the nitrogen are partially negative. So, for example, in this case, we have a carbon-chlorine bond that is polarized. The partially negative center of the nitrogen in ammonia can attack this carbon and therefore kick out this chlorine and replace it itself. And in that way, it actually produces a amine. Okay? Or all those haloalkanes, fluoride, bromide, or iodide, can also react in similar ways. Okay? So the general equation shows the actual reaction will actually happen, the pattern, the type that we want to memorize. That is, ammonia substitutes haloalkane, the halogen on the haloalkane, to produce amine. Also, hydroxide can react in similar fashion. So the hydroxide ion, when in a reasonable or significant concentration, can attack the partial positive center of this carbon here and kick the chlorine out. And in the end, it will produce chloride as a byproduct. That's not what we want. And an alcohol. Alcohol is something that we really want in organic pathways. So the general equation works in this way. You can see that inorganic reactants in this reaction pathway is written as a condition, and inorganic products are omitted. We do this when we want to simplify and emphasize the organic parts of the reaction, namely like organic reactants and organic products. So written in this way, it's not a full equation, it's more of a reaction pathway. It helps us to really see what's happening. And when we have multiple steps of organic reaction happening, it helps us to keep track of the organic reactants and products that we really want. Okay. So let's go back to the substitution of haloalkane in basic environment. Because it's a basic environment, so there must be a reasonable concentration of hydroxide. Water, for example, cannot react with haloalkanes in such an easy way. For water to substitute haloalkane, a catalyst is required due to the low concentration of hydroxide. So I want to remind you of what we learned regarding the rate of reaction. That is, lower concentration of reactants will result in low rate of reaction. So to make this reaction happen at a significant reaction rate, then we need a catalyst. But even a catalyst is used, this reaction is much slower. So if we really want to produce alcohol, we are advised to use a base like sodium hydroxide solution to react with haloalkane. we are advised away from using water straight away to produce alcohols from haloalkanes.